All right, so maybe I'll slowly start. Good morning, everyone. Thanks a lot for being here. I'll start by reminding ourselves of what we have done last time. Oh yeah, first I would like to say, remember that there is a, I'm happy to get feedback directly whenever you can, but there is also this online form you can fill if this is easier for you. I put a link on my webpage if you don't remember it. So yeah, I want to start by reviewing briefly the very last thing we have done last time. I rushed a bit through this discussion on the generalized version of the Curie-Weiss model, so I want to go through it one more time today. So the way we extended the definition of the Curie-Weiss model is that we, instead of the square function being here, we took a general function psi. And I should have said, let's say the function psi is smooth. Okay? I don't care to optimize over the regularity of this guy. So I think continuity will be fine, but let's say it's smooth. This is a sum from 1 to n. Okay? I don't write it each time. Okay, so if you replace by the square function, you recognize the energy of the Curie-Weiss model. And then the second thing we made to generalize the Curie-Weiss model is that instead of writing this 2 to the minus n sum over sigma in plus 1 minus 1 to the n, we just write a general probability measure. Okay, this Pn. This is a probability measure on Rn. Sigma is a vector in Rn. This is coordinates of sigma. And we just assume that the support of this measure is in a ball of radius Scoven, centered at the origin. And the important assumption we make is the one written here, which is that when we set t equals 0, where you see that then you're only calculating a log Laplace transform of this variable sum of sigma I under the measure Pn. Then we assume that this is convergent to some function psi, and that this limit is C1 as a function of h. Okay? And this, we make this assumption so that it fits with what we have seen in large deviations. So when this assumption is valid, we know that under the measure Pn, this random variable sum of sigma I, maybe normalized by n, satisfies a large deviation principle, and the rate function is the convex dual of the function psi. And once we understand this large deviation principle for this guy under Pn, we can infer the behavior of this guy as n goes to infinity by a sort of decomposition into all the possible values that random variable takes. Okay? And so when we do that, we discover that in the limit of large n, the free energy becomes that optimization problem. Okay? You recognize exactly the same form. You see t psi of m. Okay? So this is kind of calculating for you this expression here, kind of conditioned on or restricted to the situation when this guy is approximately equal to m. So of course here you get t times psi m, then you get hm, and then this is the cost, or like the number, it measures the size of the probability that random variable takes value m, or if you like, if you forget about the exponential and replace by indicator function, that guy is approximately m, that will be exponential minus n psi star of m. Okay, so I hope that when you see this formula, you find it kind of convincing. Okay? And there is a rigorous proof of this statement in the notes. I think it's theorem 2.19. Okay, so this is what I wanted to say. So why do I want to discuss this generalization rather than just stick with the standard Curie-Weiss model? Yeah, is there a question?
Quick question. So can I think of that convergence assumption for the Fn0h as saying that sigma, that Pn assigns relatively large probability to sigma, I guess, having L1 norm at n. It means that this
sigma having L1 norm n? No.
I mean the sum of sigma I being n with reasonable order n.
Not necessarily. For instance, if Pn is concentrated on the, like if Pn is a Dirac mass at 0, then the statement is still going to be valid.
You also impose that the model of sigma has to be
Yeah, but 0 is in the ball, so this is fine. So in this case, if you imagine Pn is a Dirac mass at 0, then what you'll get is that, okay, so I guess psi will be constant equal to 0, and then the dual will be plus infinity except at 0, and it will still be fine.
So
okay.
What kind of things does this condition rule out? I'm just trying to get my head around.
The C1 thing, you mean?
For example.
Well, convergence, you have to have some consistency of these things, otherwise you cannot hope for a convergence, right?
Sure.
And then I guess the key question is, why is this C1 assumption important? And then if you work out the counterexample I gave you for the large deviation principle, you can also work out the counterexample in this circumstance also. In general, if the C1 assumption is not valid, then you cannot infer the actual large deviation rate function for that variable. And so then, this would be a guess for the large deviation rate function. You're making that guess, but maybe this is not the correct large deviation rate function, so you're getting it wrong. Are there other questions or comments? All right. Yeah, so the reason I want to discuss this generalization is that it gives us a broader set of models to think about, and we see that when we come to our PD techniques, it's going to be very interesting. And also, even from a purely statistical mechanics point of view, it's kind of interesting in my opinion, because you can see that by playing with psi or with these measures, you can engineer lots of different types of behaviors. For instance, in the standard Curie-Weiss model, we discussed there is a sort of phase transition. There is this critical, now in this notation it's critical T, such that some discontinuity emerges. But you can decide, you can find some psi for which you will have just no phase transition, or you can have multiple phase transitions. They can occur not necessarily at 0. In the Curie-Weiss model, when the discontinuity shows up, it shows up in a sort of continuous way. First there's no discontinuity, and then it progressively increases near 0. But you can also engineer transitions where you directly jump from no discontinuity to a sizable discontinuity. Anyway, I think it's interesting to let's say realize or explore models where you have this variety of phase transitions that can go on. And okay, perhaps a last word of comment. When you want to study this quantity, I mentioned yesterday the envelope theorem. I think it's a very useful statement to know its validity of, let's say. And so I encourage you to check out this envelope theorem in the notes. I think it's theorem 2.21. I think it's just interesting whether or not you like statistical mechanics. Okay, so that will be, now I'm going to switch to a new chapter. And the reason I want to switch to a new chapter is that so far, in some sense, I gave you two things. I gave you one possible way to get large deviation principles. And the thing I told you is sort of like, if you can compute the free energy, then you can infer the large deviations. It's like if you know the log Laplace transform of Sn, kind of a free energy sort of thing, then you know the large deviations of the thing. And then later I told you, if you know the large deviations, then you can infer the free energy. So it's cool and nice and good, but here we found a trick because there is some simplification because this variable, like this part, we can rewrite in terms of this, but in general, you just have a bit of a circle that you cannot really break. So we need to develop new techniques in order to not just hope for large deviations to save the day all the time. Like we need to find techniques to just figure out what is the limit for energy in some different way. Does that make sense? And so I think there are several things you can explore, but the one I'm going to try to present here is one based on partial differential equations. So today we're going to start to talk about partial differential equations. So let's say it's chapter 2. And it's going to be about Hamilton-Jacobi equations. Okay, it's just the name of the PDEs. Oops. And to motivate this, I'm going to go back to the standard Curie-Weiss model. Okay, so maybe I'm going to rewrite the definition. Okay, that was the definition of the free energy. What do I want to do? Yeah, perhaps I also introduce this notation for the Gibbs measure associated with this energy function. So the bracket of a function g of sigma, by definition, is sum of g of sigma. Okay, maybe I had put 2 to the minus n. Sum of g of sigma exponential of that thing above divided by the sum of exponential of blah, blah, blah. Okay, and well, I told you that now I'm going to try to shoot for partial differential equations. So how about we compute some derivatives just to see what happens. We already computed the derivative in h, you remember? Let me write this one more time. So if I do the calculation explicitly, this will be, so there's 1 over n in front, and then sum over, okay, 2 to the minus n, sum over, yeah, maybe I'm not going to write the 2 to the minus n because it will be also in the denominator, sum of sigma I, so this is sum over I, this is sum over sigma, exponential of blah, 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 divided by sum over sigma of exponential of da, da, da. Okay, so and this we can rewrite more succinctly as this average, like this. Okay, so far so good. And the same thing happens if I differentiate with respect to the t variable. So dt fn is 1 over n sum of sigma I squared. Okay, I directly wrote it, but it's this guy that is going to pop out. So there's already a 1 over n here, and then I get an extra 1 over n here, sum of sigma I sigma j, which I rewrite like this. Okay, so if you are not paying close attention to the expressions, maybe you start to think that this actually is the square of this guy. Okay, it's not quite true. The square is inside the bracket, but maybe this is still something interesting to think about. So let's look at this difference more closely. Maybe I'll rewrite it. So this is 1 over n sum of sigma I, everything squared, minus the average of 1 over sum of sigma I, and then squared. So yeah, it's the variance, of course. Maybe I'm going to write like this, because this is variance with respect to the Gibbs measure of 1 over n sum of sigma I. Okay, and so this quantity, this random variable, 1 over n sum of sigma I, for sure is going to be between minus 1 and 1. And you know, if you're a bit optimistic, you think, I'm summing a lot of random variables. Not sure if I understand the Gibbs measure very well, but okay, you know, in many instances we have cancellation, so maybe as n goes to infinity, this variance will be small, in fact. Okay, and that's kind of interesting because you start to think that maybe as n goes to infinity, you're going to have that this is actually basically equal to 0. And so you will get a partial differential equation for fn in the limit of large m. Okay, and this is what we're going to try to shoot for. So this gives you a sort of evolution equation. That's why I called this parameter t, because I kind of think of it as time now. This is kind of this propagation thing. And so if you believe this is true, then maybe you start to also be curious that we can understand what happens at t equals 0, because then you have a full description. You have t equals 0, you have the evolution equation, and maybe we will be done. So let's see what happens at t equals 0. And we kind of already did it a little bit, where I kind of recalled it even. When t equals 0, this disappears. So you just have this term. And maybe it's not super obvious when I write this thing as this sum, but remember this sum, you can interpret it as an expectation with respect to the product Bernoulli measure. And exponential of a sum is product of exponentials. So you're doing an expectation of a product of independent random variables. Everything factorizes. And in fact, this quantity, when you set t equals 0, does not depend on n. Okay, so this is f1 of 0h, which maybe I'm going to denote psi of h by analogy or by, like, to make it consistent with the theorem I left on the board here, which I'm going to erase now. Okay, so we are hoping that as n tends to 0, we can make sense of what I just said. Whoop. And so we are starting to wonder a bit more about this variance. What can we say about it? Can we say it's small? And in some sense, this is really the Laplace or log Laplace transform of the random variables. So in some sense, it should also encode one way or another the information about this random variable, all of it, including the variance. So it should be possible to rewrite this term just in terms of Fn, because Fn kind of contains this information. And I'm not going to keep you in suspense. I'm going to just differentiate a second time this with respect to h and see that this is going to tell me something about the variance. So let's do this calculation. dh2 Fn. So that's the expression for the first derivative. Let's stare at it for a second. Where is the h? Nowhere. OK, it's in the dots that are not written here. OK, so please project this down there. So there's an h hidden somewhere here, and another one hidden somewhere here. OK? So when we differentiate, well, OK, there's one term when we differentiate the numerator, one when we differentiate the denominator. In the numerator, we'll get an extra sum of sigma I showing up. So let me write that. 1 over n sum of sigma I, everything squared. That's the numerator part. And then in the denominator, when we differentiate, we'll get yet another time this expression. So we'll get that guy squared. And then, we have to square the denominator, so we'll get that guy squared. So it will be a bracket squared of the sigma I. So plus or minus, 1 over n bracket sum of sigma I, everything squared. Agreed? Okay, I wanted to do this calculation a little bit carefully because I want to emphasize the scaling, which is very favorable to us here, because this is n times the variance of the random variable over there. So see, n times variance of 1 over n sum of sigma I. Okay, so that's what it is. So what we have just found here is that, and again, this is really the magic of the Curie-Weiss model, is in general, perhaps my hope is that in the limit of large n, we discover a partial differential equation that looks nice. But for the Curie-Weiss model, it's really very nice because even for finite n, we can write an exact partial differential equation in terms of Fn only. Like this. Make sense? And I remind you that also Fn of 0 dot is psi all the time. And now, when we see this, it feels even more convincing, I guess, that at least oftentimes this will be small as n goes to infinity. Okay, so we have seen the sort of function we expect in the limit, and it's not entirely clear that the limit will be smooth everywhere. But if you think about it, it's going to be convex, and so it's not possible that this is like divergent at every single point. So at most points, this will have to remain reasonable, and maybe there are a few exceptions. And perhaps I could also work you through this, but in fact, because we have this large deviation technique, we know in advance what is the answer. And because we have this envelope theorem, also we can express the derivatives in t and in h. And so if you manage to do this calculation in your head, we saw that if there's a unique optimizer in the formula, the derivative in h is just the value of that optimizer. And the derivative in t is going to be the square of that guy. And so, because in the formula you have t times m squared. So when you differentiate with respect to t, you get m squared. And so we have seen that as long as the limit is, like at every point at which the limit is differentiable, we have the relationship that the t derivative is the square of the h derivative. Okay, so let me write this. We expect fn converges to f with, let's say, where f satisfies dtf minus dhf squared equals 0 almost everywhere, and f of 0 dot equals psi. And I think now it's a good time for me to add one piece of information that is useful when you start to think about this, which is that, so remember that all of our functions are Lipschitz uniformly over n. So in particular, the limit will also be Lipschitz. Okay? They are Lipschitz because you see the derivatives, you stare at the expression, you see it's bounded between, here this one 0 and 1, and the other is between -1 and 1. And yeah, the piece of information I want to remind you is that every Lipschitz function is differentiable almost everywhere. So here, perhaps if I wanted to be a bit more precise, I could add that f is Lipschitz, because that's kind of clear. And therefore, it's differentiable almost everywhere. And maybe I could specify that at every point of differentiability, this is valid, okay, which is in particular almost everywhere. All right, so this sounds like a good plan, in my opinion, at least. But the question that arises is this a complete characterization of a function? If you just, if I just tell you I have a function, it satisfies this, can you conclude that this is the one we were talking about when we were using our large deviation technique, for instance? Is that true or is that not true? Because if it were true, we would have a good program or a good alternative strategy to identify the limit, because we would just do, I didn't give you a full proof, but basically we have good ingredients to try to prove it directly like this now. Let me see if I can. Yeah, unfortunately, the answer is that this is not the case. So there are many functions that satisfy what is written here. So let me try to convince you of this. I'm going to explain that. I'm going to explain this in the situation where I replace the initial condition, this function psi, by 0. Okay, so yes?
Could you explain once more why the right-hand side, it should go to 0?
Yeah, so I was a bit sketchy. So I think you have two choices to try to convince you that this is plausible. One is to exploit that you know in advance what f should be, and try to verify that indeed the f that we have found satisfies this. And if you want to do that, you can say, well, the f we have is Lipschitz, so it's differentiable almost everywhere. And at points of differentiability, you can use the envelope theorem and check that it's true, because this is m squared and this is m, and then you square. Alternatively, you can try to use that expression and try to justify this is fine. And this is a bit more, I didn't explain very much, but the thing that you want to exploit is that the thing is, the function fn is convex. And so this guy, it has to be non-negative, and you cannot make it be big all the time. So you can exploit that when you integrate over an interval, it has to give you a finite value, for instance. So it's a bit more delicate. You have to work it out a bit more, but there might be points where this is big, but you can kind of rule out that they are big in a big part of the space. But yeah, this requires more care, and I don't explain it very well. Other questions? Or? Okay, so let me go back to this. So, yeah, so what I want to convince you of now is that this is not a complete characterization of a function, and I'm going to demonstrate this in the example when, for the initial condition, we take the function 0. Okay, so if the initial condition here, if the function psi is replaced by 0, there is one function which clearly is a solution. It's the 0 function. Okay, 0 is a solution, no problem. And so I have to give you another solution to this equation with 0 initial condition. And perhaps before I do this, let me give you two solutions. Let's forget about the initial condition for a second, and let's explore what simple functions solve this equation. So we see the 0 function is 1. Okay, I'm just writing it like this. And then I can also, if I do t plus h, I don't need to put parentheses, then this will also solve that part, okay? Not the initial condition I care about, but the first line will be valid. And also th maps to t minus h is also a solution, right? With the wrong initial condition, but. And so now I'm going to try to build my counterexample by patching these solutions together in the following way. So I start from the 0 initial condition, and then I'm going to, so here I'm making a drawing for fixed t, and I'm drawing the function as a function of h. And so at t equals 0, we're going to be flat at 0, and then I'm going to create a corner with these slopes, and I'm going to let the corner go like this. So at time t, I will see something like this. Push, push, like this is t. This is minus t, this is t. So this is t plus h. And this is like h maps to t plus h, and this is h maps to t minus h. Yes, I think that's correct. Does it make sense, what the function is? And so I claim that this is a solution to, like this satisfies these two properties with 0 initial condition that is sure. And why is it almost everywhere a solution? Well, it's because except for these places where there is a corner, by definition, I chose a solution, so it solves the equation. Okay. Does that make sense? And you see that, okay, so now we have two solutions, but once you have this one, you can engineer many of them. Like for instance, you don't need to center this function at the origin. So you already have an uncountable number of those. You don't need to let the corner start at the initial time. You can wait a little bit. So that's also freedom. Anyway, we see that this is not going to be, yeah, we have many enemies to fight against, let's say.
There's some sort of Peano phenomenon, no? Like,
yeah, anyway, you have lots. Like, yeah. And so our notion of solution is too weak, like it's too permissive in some sense. So we can go back to this. Here we said, oh, you Lipschitz and you solve the equation almost everywhere. Perhaps one way to make it stronger would be to say, okay, we want this to be satisfied everywhere, not just almost everywhere. So then we would have to ask that f is differentiable everywhere, or C1 maybe. And to solve the equation everywhere, that would be a stronger notion of solution. And then indeed the solution would be unique. The problem is that maybe it will not exist. Okay, and I think we have a good sense of why this might be occurring, because we know that the function we care about is not differentiable at some point. You know, initially maybe it stays differentiable, but then it wants to create a corner. So if we say that the solution that we want is differentiable everywhere, we are ruling out the one that we care about. That doesn't sound like a good sign. And okay, so we have to sneak in between these two notions something which makes the solution exist and be unique at the same time. Okay? Just between being Lipschitz and being C1, something a bit extra than just saying you solve the equation almost everywhere. Make sense? Yes, and And the mechanism by which we are going to try to get this is by trying to recall the sort of approximations that we come from, where there was this extra second derivative hanging around, let's say. So perhaps a remark. If you have two functions, maybe I'm going to write like this. Maybe I write like this with some epsilons. If you have two functions that are like this, and that initially one is on top of the other, let's say f was smaller than g, for the initial time, this is t equals 0, then you can show that this is going to be preserved as you let the time flow. Under reasonable circumstances, let's say. Okay. Then this is the maximum principle, and this is something that we want to be preserved for our new notion of solution. Okay, we want that, in some sense, our notion of limit remembers that it comes from things that look like this. Okay, so I want that, in some sense, our definition allows us to recover properties like this of monotonicity. If you have a comparison at initial time, I want this to be preserved along the evolution of our notion. Okay, so the exact definition, so the notion that will make this work is called the viscosity solution. And in the exact definition we give, we don't immediately see that this property is valid, and so then we will just prove it as a theorem later. Okay, but essentially, the goal is to encode that we want a property like this to be valid. Make sense? Maybe I'm going to erase and move to defining this. Whoop. I haven't converged yet. So I'm not going to only focus on the square function. Maybe I'm going to also erase this while I'm here. So we're going to discuss equations of this form, where the nonlinearity, the square function, is replaced by some generic function. And maybe we don't want to stick to one dimension, so maybe instead of h, we'll have some variable in Rd. Okay? So where was it? Maybe it's that was motivation part. Now it's this definition of viscosity solution. Okay, so I give myself a nonlinearity. For instance, the square function in the case that we care about. And for the Curie-Weiss model, we think that d is equal to 1. Okay, this is where the h variable is living in our head. I say local ellipses, but okay, in practice, everything will be smooth for us for this function. So don't worry about this assumption. And yeah, the goal is to study, let's say, the well-posedness, like existence and uniqueness of solutions, at least, of and in fact, I'm mostly going to focus on the uniqueness part, because this is really what we are missing in order to complete our argument for the Curie-Weiss model. Okay, existence is going to come for free because we have our function fn around and we can extract subsequences, etc. So really it's the uniqueness that I want to worry about. Okay, so now f is is a function of t and x. I'm going to write like this from r plus cross rd, taking values in r. And the derivative with respect to x is gradient of f. Okay, the gradient is only taking the derivative with respect to this x variable, not with the t variable, which I denote like this. Okay. Perhaps oftentimes I'm going to refer to this equation as this guy as being the Hamilton-Jacobi equation, or like HJ. If I need a shorthand, I can just write this. Okay, so again, I'm going to try to build so I'm not going to directly splash the definition on the board. First, I want to try to motivate why the definition makes sense. And for this, I want to remember that we want to exploit that before we pass to the limit, we had this little bit of Laplacian going around. Okay, so let's think that we have some function f epsilon, and maybe it's Lipschitz, it's smooth, just like in the Curie-Weiss model. And it satisfies this, well, this is the Laplacian. Okay, the sum of the second derivatives of f epsilon in the x variable. Okay, and let's assume that this converges to something. Let's just try to explore what properties we can say about that limit. Okay, suppose that f epsilon converges to f. And yeah, maybe I'm not going to, so this is just intuition part, okay? I'm not being very precise. But if you think again about the Curie-Weiss model, we know these guys are uniformly Lipschitz. You can use Arzelà-Ascoli to justify at least up to subsequences, you can do that. And then the notion of convergence is locally uniform over the space, okay? So suppose this occurs, and we want to, we have just seen that if we just say what this does at points of differentiability, this will not be enough. So we want to also say things about what happens at points that are not points of differentiability of f. And so we would like to talk about the derivatives of f at this place, but it's not differentiable, so how do we do that? Maybe you have seen that oftentimes in PDEs we try to push the derivatives onto some test functions that are smooth. We're going to try to play a game a bit like this here too. But oftentimes this is used in a way, like it's done by using some integration by parts, like you integrate against Lebesgue and you try to do some integration by parts. And this is not what we're going to do here. There will also be a sort of test function going around. We're going to try to push the derivatives onto it, but not using this integration by parts trick, which you may or may not have seen. If you have not seen it, then no problem. And perhaps the reason is that this comparison principle I described very briefly is more about comparisons at a given point. So we are going to try to rather test what happens when we compare two functions at a given point and see if we can say interesting things. So what does this mean? So let's take, let's say that phi is a smooth function. A function of t and x, like f is. And let's say that we have a special point. I'm going to call it tx still, in 0 plus infinity cross rd. And I open the interval for t. I don't want it to touch the boundary. Let's assume that we have a function like this, and the point where f minus phi has a local maximum at tx. Maybe a strict one even.
Do you suppose phi completely supported or just CT?
It's infinity. Okay, so let me do a drawing. So f maybe has corners. Okay, so Lipschitz function. I can draw it like this. This is f, and I'm touching phi Okay, maybe I'm going to draw like this. Yeah, so here I'm even assuming that the value of f minus phi at tx is 0 implicitly, but I hope I did it correctly. F minus phi is maximal at this point, okay? Okay, so when I do these drawings, I always try to put a corner on the function f because it's Lipschitz, and the smooth guy is the function phi. And we have a local maximum. In fact, we're even 0 on this drawing, and otherwise it's negative at tx, okay? This is tx. So this f minus phi here is 0, and otherwise it's negative.
Okay, let's see.
Okay, so let's suppose this occurs, and let's try to see what we can say. So f is not very smooth, maybe it's only Lipschitz. So let's try to go back to speaking about f epsilon. Because it's a strict local maximum and we have this convergence, we can find a point close to tx such that f epsilon minus phi also has a local maximum at a point nearby. So let's say there exists, we can find t epsilon, x epsilon going to tx as epsilon goes to 0, such that, at least for epsilon small enough, f epsilon minus phi has a local maximum at t epsilon x epsilon. Okay, if you're not quite sure why this is true, I mean, it takes, I think it's good to be careful why this is true, but this is done in the lecture notes, so you can check that this is valid. And otherwise, yeah, I hope it's kind of intuitive that if you have a function that is kind of close to f, you will have something like this occurring. And now we are dealing with smooth functions, so we can just say that at the contact point, the derivatives coincide. And we can also say things about the second derivatives. So let's write this. So dt of f epsilon minus phi at t epsilon x epsilon is 0. The gradient of f epsilon minus phi at t epsilon x epsilon is 0. And also, well, I could speak about the whole Hessian, but let me just look at the Laplacian of f epsilon minus phi. I mean, think of it as being in one dimension, if you like. The second derivative of this thing at the maximum has to be non-negative, right? If it's pointing up, then we have a contradiction. So this has to be, I said non-negative. Yeah, I should not have said that. It has to be negative. Okay, let me keep using French convention here. Non-strict inequalities are implied when I say negative. Okay. And so now my goal ultimately is to look at derivatives of phi. I'm telling you that I'm trying to push the derivatives onto phi. So can I say anything about the derivatives of phi minus h of grad phi? If I try to compute this at the contact point, t epsilon x epsilon, so we just said that the first derivatives are equal whether I put phi or f epsilon, so I can substitute. And now f epsilon satisfies this equation, so I can write it. Okay, I can use this relationship. This is epsilon times Laplacian, f epsilon of t epsilon x epsilon. And I would like to send epsilon to 0, but I'm worried that this might blow up. I don't understand how this behaves as epsilon goes to 0. But at least I have this inequality. I can compare with phi. So this is going to be smaller than epsilon Laplacian of phi at t epsilon x epsilon. And now phi is smooth. So t epsilon x epsilon converges to tx. In particular, it stays in a compact set, no problem. So this will remain bounded as epsilon goes to 0. So the whole thing goes to 0. And here phi is smooth again. So if I pass to epsilon goes to 0, I get just tx here. Everything works out nicely. And so we conclude that as epsilon goes to 0, we conclude that dt phi minus h of grad phi at the original point we cared about, tx, whoops, tx is smaller than or equal to 0. Okay, so just to recap, okay, so here we had, I made a drawing where f had a place where it's not differentiable, but we said, oh, whenever we can touch it from above, which basically means whenever you can put a tangent like this here, the slope of that thing has to satisfy a constraint too. The constraint is written here. So you see, we're adding an extra constraint even at points where f is not differentiable. We're saying, like the set of slopes that are on top of f has to be like so. Okay. And so this will be the source of the extra, we are adding this extra constraint, and this is why we're going to manage to get uniqueness in this. I thought I wanted to say something else. Yes. One last word of comment. When I write things, I say f minus phi has a local maximum or strict local maximum. When I draw things, I often make them touch like this. And when I speak, I already said it a couple of times, maybe I shouldn't have. I say, oh, where they touch. And the reason I allow myself this, let's say, abuse of language is that we're only doing calculations at the levels of derivatives. So I can always add or subtract a constant. So in my head, I really think that what we're doing is basically we're choosing a slope and we're kind of sliding until it touches. And this selects the point of contact. And this is the point where we're going to make the argument. Okay, so I say, contact point, touching, and these sort of things. Even though when I write, I just write local maximum or things like that. Okay, so what we have discovered here will be the definition of viscosity solution. Okay, we're going to say your viscosity solution is if whenever I can touch it from above, the slope that I find here satisfies that property. And okay, this is only one side, but we're going to say it on both sides. That will be our definition of viscosity solution. Let's remember our equation Hamilton-Jacobi, Hj. We want to make sense of being a viscosity solution to this thing. And so let's give ourselves a function defined in the right place, like r plus cos rd, taking values in r. Let's just assume it's continuous, and I want to make sense of it being a solution to this equation in just the way we have seen. So I'm going to write it like this. So we say that f is, so I'm going to use one word for just satisfying the property we've seen, another word for the property where we touch from the other side, and then solution for when you have both. So f is a viscosity subsolution to the equation that we care about right now. If for every, how should I write this, tx and every phi in C infinity. Yeah, I don't write the domain, but r plus cos rd would be fine. Phi in C infinity, such that f minus phi has a local maximum at tx. We have dt phi minus h of grad phi at tx is smaller than or equal to 0. Okay, so I'm lucky that we've just done the heuristic derivation, so I remember that local max goes with things like this. But when I don't do the heuristic derivation just before, what I do is that I make this drawing with the f being like this and the smooth function phi being on top. And for once, I created a bit of space here. And I think that when we touch from above, we're trying to control the growth of f from above. So we're going to try to push f towards going down. And so I think that the t derivative should be smaller than or equal to 0. Because that's kind of my I don't know, way to remember. All right, so this is sub-solution, and now super solution will be just the exact other way around. So maybe I'm not going to rewrite entirely the whole thing. So we say that f is a viscosity super solution. To hj again. If for every and every phi smooth, such that f minus phi has a local minimum this time. Okay, this is where it changes. At Tx, we have the converse inequality, dt phi, minus h of grad phi at Tx is greater than or equal to 0. Okay, does that make sense, my horizontal lines? All right, and now your solution if you're both a sub-solution and a super solution. Okay, and sometimes I forget to say viscosity, like for instance here. But okay, I always mean viscosity subsolution, viscosity super solution, and I should say, at least here I should write it, F is a viscosity solution if it is both a viscosity, okay, let me do it, subsolution and the viscosity super solution. Okay. Okay, so I did a little change compared with what we have done in the heuristic derivation, which is in the heuristic derivation, I used strict local maximum, so that when I was doing my going back to the epsilon, I had a bit of room to make sure that even when there is epsilon around, I still have a local maximum. And I did not write it in the definition, but you can check that this definition or the definition where you put strict here are equivalent, in fact. So there is one side which, one definition is stronger than the other. So let me try to process this. Yeah, so imagine you're only given a function that satisfies the definition with the strict here in the definition. And now you're touching it, and you only know that f minus phi has a local minimum, but you don't know it's strict. What do you do? Well, what you can do is just bend phi just a tiny bit to give you an extra bit of room. Maybe you add a parabola to phi so that you don't change the value of the derivative at the contact point. But then you know that you become a strict local maximum because except at the contact point, you have put your new function a bit above. Okay, so these are equivalent. Okay, this is worked out also in the lecture notes in detail. So let's say replacing local max by strict local max. Give equivalent definitions. That's one thing. And also, yeah, this we didn't play with, but I use test functions that are smooth. But if you want to use test functions that are just C1, this also gives you an equivalent definition. And again, you can argue by convolution or something. You can make some argument around this. So. replacing phi in C is in C infinity by phi is in C1 in the definition yields an equivalent definition. Okay, again, this is worked out in the lecture notes. Okay, so perhaps what we could do first is check that indeed this new notion of solution is sandwiched between the two notions we had explored earlier. So let's start with, suppose that I give you a function which in fact is C1 and solves the equation everywhere. Then we should be able to assert that it is a viscosity solution. And what happens is that when you have a function like this and you have this situation with f minus phi having a local maximum, then the derivatives of f and phi will coincide at the contact point. F, we said, should be a solution in this case, and so you will know that this is in fact even equal to 0. So indeed, if you're C1 and you solve the equation everywhere, then you are a viscosity solution. Now, conversely, if you are a viscosity solution, hopefully you solve the equation almost everywhere. Now, this is a little bit, maybe it takes a little bit more time to show, but this is also true. So the way you can do it, okay, at least if you're a Lipschitz, let's say you're a Lipschitz viscosity solution, then this is true. So if you're Lipschitz, you know in advance that you're differentiable almost everywhere, and then what you want to argue is that at points of differentiability, if you're a viscosity solution, in fact, you solve the equation. And this, again, you can do because you have to argue that at the point of differentiability, you can find a function which is in C1 with which you can touch. And, okay, you have to do the argument, but it's true. So at least, the sanity checks are good. We wanted something in between the two notions of solution we had explored at the beginning, and that fits the bill. Okay, so maybe I'm going to postpone a little bit the verification that this notion of solution gives us a unique solution for our equations. And first, I want to verify that when we come back to the Curie-Weiss model, indeed, we can assert that at least any limit, any subsequential limit of Fn will be a viscosity solution to the equation we are thinking about. So let's say back to Curie-Weiss for a little bit. Okay, so the first thing I already gestured at this a couple of times, but let's convince ourselves that this is true, that we can extract converging subsequences, that the sequence of functions of Fn is pre-compact. So yeah, this function Fn for the Curie-Weiss model, we've seen that it's Lipschitz with Lipschitz constant equal to 1 in both variables. Maybe I should say it's equi-Lipschitz or something, uniformly over n. Anyway, I just mean it's uniform over n. And we've also seen that Fn of 0 dot does not depend on n. Okay? And if you remember the criterion for the Arzela-Ascoli theorem, you have to check like a uniform equicontinuity of your family of functions, which is clearly implied by that property. And you have to check that at least at one point, the set of the functions evaluated at a point, they don't just diverge to wherever. And here we have it even at many points. Okay. So it does not depend on n. So with these two pieces of information on the board, you can right away apply the Arzela-Ascoli theorem. And the accent on Arzela maybe is here. Maybe it's like this. Okay. Like the other way around. Okay. Sorry about this. Fn is pre-compact. Okay, by this I mean you can always extract converging subsequences. Okay, and the topology is that of local uniform convergence. So yes, extracting subsequences is fine, and now the claim is that any subsequential limit is a viscosity solution to the equation. So let's say, suppose Fn converges to F along a subsequence. I don't specify, but when I speak about this sort of convergence, I always mean for the topology of local uniform convergence. And then F is a viscosity solution to dTF minus dHF squared equals 0. Okay? So, yeah, I was planning to give you the argument, but I'm hesitating because I was hoping to do more things. The reason I consider not doing the full proof is that I consider that I actually already gave it to you. Because when I gave you the intuitive argument to motivate the definition of viscosity solution, I was in fact exactly in this setting where the object we care about, before we have this sequence of functions, and they satisfy this equation with a little bit of Laplacian. So here there's just one dimension, so a little bit of a second derivative. And so, we are really exactly in the setup of the informal argument, which was not so informal after all. It was, you're really in a setup where you can just apply it here. Okay, so yeah, I think it would be perhaps not lost if I was doing it again, but perhaps I will leave it to you just for the sake of time. Is that okay, or do you at least have a sense that this will look similar? Okay, you see that Fn, we know in advance that, let me write it here, dt Fn minus dH Fn squared equals 1 over n dH squared Fn. So this is really like epsilon Laplacian of the guy, okay? And it's just epsilon has become 1 over n, but that's it. Okay, so it's really the same argument. So in particular, at least for our purposes, we'll never worry about existence of viscosity solutions because we already have our favorite statistical mechanics model around that wants to converge, wants to be a viscosity solution in the limit in some sense. So, the problem is that we want viscosity solutions to solve is the uniqueness part. Okay, but existence is kind of for free from that thing. We have already our Curie-Weiss model in the pocket, and that gives us existence in some sense. Okay, so I'm not going to explain then the general theory of existence for these equations. And now I want to talk about uniqueness. Let's say this is 3. So we're going to show something in the style of this maximum principle argument I was kind of gesturing around at the, like some time ago today. So we are going to prove something which is stronger than uniqueness and which is going to be very useful for a variety of reasons. Let me state it. It's really a monotonicity property, the fact that if two things are ordered at the beginning of time, then they will remain ordered forever. So the theorem I'm stating is the comparison principle. let U be a subsolution and B be a super solution. So now I'm back to the general equation, this HJ equation. Okay, not necessarily the square nonlinearity that we discussed there. And maybe I'm going to assume that they are both Lipschitz continuous. This is not really necessary, but well, okay. At least it's very convenient for the proof. And we always have it for our models, so this is fine. The space variable, I mean x, okay? So I have two functions. I don't really assume they are both solutions. I just assume U is subsolution, V is super solution. And I also assume they are both Lipschitz in the space variable. Okay? Yeah, again, this is not necessary, but we have it anyway for all our examples, so let's just take it. So the claim is that if you look at the supremum of U minus V over R plus cross RD is going to be equal to the supremum when you restrict to the initial time. Okay, so again, when I say things, oftentimes I think of things as touching or as comparisons, but when you phrase things, you can phrase things up to a constant, and okay. So let's imagine that you know that at initial time, U is, how should I set it up, above V. Is this what I want? It's positive. No, that doesn't sound right. Yeah, I say it wrong. Suppose that U is below V at the beginning. Then that supremum is negative. And you're learning that the supremum remains negative even if you optimize everywhere. So U will remain below V. Okay, and that also is in line with the intuition that a subsolution really wants to sort of go down compared with the real thing, while a super solution kind of wants to go up compared with the real thing. Okay, so that's what it says. So in particular, if U and V are both viscosity solutions, dt and they coincide at initial time, U of 0 dot equals V of 0 dot, then U equals V. Okay, maybe this is what we were most hoping for when I was speaking about uniqueness, and we can check that it's true from the statement. Let me just walk through it. If U and V are both viscosity solutions, and in particular U is a subsolution, V is a super solution, at initial time U is smaller than V, so this remains true forever. And then we can interchange the roles of U and V, so you also conclude that V is smaller than U forever, and so that gives you U equals V. Okay, so maybe now I'll take some time to motivate how we're going to prove this, and I think this is really an important ingredient in our strategy, so I would like to give you a full proof, okay, at least an almost full proof of this result, which might take me some time. So I think today I will only give you some intuition for how we're going to try to prove this. Maybe I can start the proof. I think if I rush to the proof, it's going to be difficult. So. So let's say some ideas. Let's just, we're here trying to figure out how to prove this statement. Let's assume for a second that, in fact, the functions u and v are C1. We can differentiate them everywhere, no problem. Then perhaps I should have said that earlier, but if you think again about the definition of being a subsolution, if you're differentiable, you can find your smooth test function at every point that you like. And so in particular, you will know that when you compute the equation for u, not for the test function, you satisfy the inequality that is displayed. So let's say if u and v are like in the statement, like u subsolution and v super solution, but also C1, then you know that you can compute this expression everywhere. This makes sense everywhere. And you know that this will be satisfying these relations. Okay, does that make sense? And again, that that is consistent with the idea that a subsolution wants to go down in time. Okay, think that it doesn't depend on space. We're saying that the time derivative is negative for u, and the time derivative of v is positive for v. Okay. Okay, so we have this, and let's suppose that we are in this nice setup, and we want to prove that this must be true. Okay, we gave ourselves more hypotheses, so hopefully we can find an argument. So, yeah, so let's try to argue by contradiction, and suppose that this is not true. When I optimize over all times, I find something better than what I get at the initial time. So in order to get a contradiction, I want to give myself a little bit of room. And so I'm going to try to engineer a contradiction between these two things. And to make sure I can have space for this, I'm going to try to make sure, in fact, not just that we are below 0, but that we are below a constant that is strictly negative. Yeah, and I can do this without destroying the assumption we are trying to contradict, because, for instance, I can say, take epsilon sufficiently small that so that if you set u epsilon to be u minus epsilon t, okay, bad notation, I mean u of tx minus epsilon t is u epsilon of tx. Then, if this occurs, then in particular, there exists a t and an x such that u minus v at tx is greater than that guy. Okay, and then I can choose epsilon sufficiently small that it remains valid even if instead of u I write u epsilon. Okay, so that I already wrote that. We have that thing being still okay with u epsilon. Do you agree that this is possible? And now I'm going to make yet another simplifying assumption. I'm going to assume that that supremum is achieved somewhere. Okay? And okay, so perhaps before I say that, let me observe that with u epsilon, what I gain is that now, if I write this with u epsilon, I get my extra epsilon of room. Okay? If I do with the epsilon version, well, I get the extra epsilon derivative here, so I will get minus epsilon instead of 0. Okay, this is the little bit of room I want to get. Yeah, and now suppose that the supremum is achieved somewhere. Well, surely it's not going to be achieved at a point with t equals 0, because otherwise there would be a problem. So t is strictly detached from 0. Is not 0. Okay. If I suppose the soup is achieved, it's not going to be at time t equals 0. And now we have two smooth functions. They achieve a maximum in some place. So their derivatives coincide at that place, right? dt u epsilon minus h of grad u epsilon at tx should be equal to the other guy. But this is a contradiction with the assumption, okay? Because they were supposed to be one below minus epsilon, the other positive, so that's not possible. Make sense? So I cheated in several places in this proof, as you can see. The two places where I cheated are when we assume the functions are C1 and when we assume that the supermem is achieved. Okay, so the goal of our real proof will be to get rid of these assumptions. Okay, I wanted to give you this sketch first because when we will write the proof, we'll have to do a bit the two things at the same time, and yeah, it's perhaps a little bit confusing if you see them right away. So I want, this is going to be the sort of the sketch, and we're going to add ingredients that ensure that we can deal with the replacement of these green parts. So for this part, we're going to use a technique or a trick that is often called doubling the variables. And for this part, yeah, we're going to, in some sense, already we observe that we can make small modifications to the function to give us a bit of space or to do some things, right? Like here we change u by u epsilon. And so we're going to also try to engineer little perturbations like this that ensure that we know that we're going to have an optimization that this supermem will be achieved somewhere. We're going to put like cutoff functions that tell us that we're not going to fly to infinity in our variables. Does that make sense? And I'm not going to, you have to fight for the t variable going to infinity and also the space variable going to infinity. And just for the sake of clarity, I'm going to give you a proof where here I'm not going to assume it's RD, I'm going to assume it's like a compact set, like maybe it's the torus or something. So I only have to fight for the time derivative that wants to go to infinity. But the full proof is a bit the same. You just have to do a sort of cutoff in both variables. And I think just doing it for one variable is enough for understanding how it works. Does that make sense? So this will be the program for next time. That's it for today.